Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous session, we discussed about the stress, strain and displacement relationships of a thin-walled open and closed section beam, and in which we consider the effect of shear forces as well. So along with the bending, we consider the shear forces, and in turn, we introduce a term called shear flow, which is the shear force per unit length, which is nothing but Q equals to tau into T, and we have seen the expression for the shear flow, and then we have made a relationship between stress, strain and displacement relationships in the previous session. Now in this session, we are going to derive a relationship for shear of open section beams, which is a derivation that we are going to have here. So it's very important. Like in the previous unit, we derived unsymmetrical bending, that is the direct stress due to unsymmetrical bending derivation. Now that is a one formula which you have to remember for solving the problems, which is a very important formula. Now along with this, is another important derivation which we are going to derive, the shear of open section beams, which is also very much important for the problems to solve, and even the derivation is also very important in the examination point of view. So let's go, I'll go and see what is the shear of open section beams. So the learning outcomes in this module are: the students are able to analyze the shear of open section beams, and the students are able to determine the shear flow distribution in open sections, like direct stress distribution what we got. So here also the shear flow distribution which we need to see. So to understand, to start with this problem and to start with this derivation, so first let's try to take open section beam, any arbitrary open section beam as shown in figure. So the open arbitrary section beam is taken like this one, and it is taken like this one, and then you try to understand the forces what we are applying on this one. So there is one force, that is a horizontal shear load Sx, and there is a vertical shear load that is acting, that is Sy, and we are taking the distribution in S direction, that is shown here, and thickness of the wall is very thin, very small, that is taken as T. Okay, so that you can assume this as, again, you consider a thin walled section. Okay, and you can see the axis system that has taken X, Y, Z axis system that are taken in this direction. So first, so the open section beam of arbitrary section shown in figure, it supports the shear forces or shear loads Sx and Sy such that there is no twisting of the beam cross section. That is very important. There is no twisting. So we are considering the horizontal shear loads Sx and Sy, and we are applying them in such a way that we assume there is no twisting of the beam cross section. So for this condition to be valid, the shear loads must both pass through a particular point in the cross section, and that point is defined as shear center, which is very important term here. What is the shear center? So shear center is a point in the cross section about which there exists no twist. So the loads that what you are applying, Sx horizontal shear load and vertical shear load Sy, so the loads are applied in such a way that they act through a particular point in the section. So if the loads are acting through this particular point in the section, if there is no twist, then that point you can consider it as shear center point. So based on this shear center is very important factor in the aircraft structures, and based on this point, the loads are been defined such that the twisting can be avoided. Okay, so it's very important for us to establish a relationship between the shear flow distribution for open section beams, and also to find out the shear center of any open section beam or closed section beam. So now here what we are doing here, and since there are no hoop stresses in the beam, the shear flows and direct stresses acting on an element of the beam wall are related by the equation dou q by dou s plus T into dou sigma z by dou z equal to 0. Now where is this equation? In the previous session, we considered the equilibrium in z direction. I told you to remember that equation that we are going to use for the derivation of shear of open section beams. What is that? We considered the equilibrium in z direction. Okay, and we represented direct stresses, shear stresses in the first diagram, and then we replaced the shear stresses and thickness and replaced by shear flow, and in which we can assume that the shear flow is equals to tau into T, and it is defined as shear force per unit length. Okay, and while you do this one, and when you consider the equilibrium in z direction, and you got this relationship, what is that? Dou q by dou s plus t into dou sigma z by dou z equal to 0. So this is the equilibrium equation in z direction. So to start with the shear flow in open section beam derivation, the first equation we have to write is nothing but this equation, equilibrium in z direction, directly from the previous session. Okay, now so in this one, it's very important, it's nothing but sigma z. Now what is sigma z? If you try to remember, sigma z is a direct stress distribution that we have seen in the unsymmetrical bending. And what is that sigma z? So sigma z equals to my Ixx minus mx Ixy divided by Ixx Iyy minus I square xy of x plus mx Iyy minus my Ixy divided by Ixx Iyy minus I square xy of y. So this is a formula which we derived for the unsymmetrical bending of the beams, which is nothing but the direct stress distribution. Direct stress distribution. Okay, so now we are going to use this, and this sigma z first of all has to differentiate with respect to z. Okay, and then multiplied by t. So that is what the equation you are writing over here. Okay, now if you try to differentiate with respect to z, let's see what you are going to get here. So if you try to differentiate with respect to z, what you are going to write? This my, you are going to write dou my by dou z, and here also mx dou mx by dou z, and here dou mx by dou z when you try to differentiate with respect to z, and here dou my by dou z. Okay, now you know the relationship, that is what you have written here. So when you try to differentiate with respect to z, and you are going to get dou sigma z by dou z, that is equals to dou my by dou z into Ixx minus dou mx by dou z into Ixy divided by Ixx Iyy minus I square xy. Now here this term dou mx by dou z into Iyy minus dou my by dou z into Ixy divided by Ixx Iyy minus I square xy of y. Okay, now after this, what we need to understand, that the relationship between shear force and bending moment. Relationship between shear force and bending moment. What is that? The shear force, the rate of change of bending moment is defined as shear force. Okay, or dou m by dou z, either dou mx or dou my. Okay, so that is nothing but the rate of change of bending moment is defined as shear force. So we are going to use the definition, but the rate of change of bending moment, that is dou my by dou z, so it gives you shear force in x direction, that is Sx. Similarly, dou mx by dou z, that going to give you the shear force in y direction, that is Sy. So now we are going to replace delta dou my by dou z as Sx, and this as Sy, dou mx by dou z as Sx, and dou my by dou z as Sy. Now we are going to replace them in place of this one and write it over here. So this you are going to write as Sx, this you are going to write it as Sy, so this you are going to write it as Sy, and this you are going to write it as Sx. Okay, so this is Sy, this is Sx, right? So replacing that, dou my by dou z as Sx, and dou mx by dou z as Sy, dou mx by dou z as Sy, and dou my by dou z as Sx. Okay, and then we are going to write the relationship for dou sigma z by dou z equals to Sx Ixx minus Sy Ixy divided by Ixx Iyy minus I square xy into x, plus Sy Iyy minus Sx Ixy divided by Ixx Iyy minus I square xy into y. So this is what you have to go and take substitute over here in the equation 1. You can assume this as equation 1, and you have to substitute. And when you try to add, so in this term what is left is t. So the t is going to add, so you are going to add t for it, yt, so that you can write t into dou sigma z by dou z, that is written, and plus what is left is this one, this term. Now this I am adding here. So dou q by dou s. Okay, and if you are writing dou q by dou s, and you can send all these terms to the right side, and you can write dou q by dou s that is equal to dou q by dou s that is equals to, and you can write, you can take out this and you can write as minus, and here also you are going to get minus. Okay, so that is, and that is for the beam element what we consider. And if you want to get over the total arbitrary, open arbitrary cross section, you can integrate this from 0 to s. So integral 0 to s dou q by dou s ds equals to, again here you are going to get integral 0 to s into ds, and again here going to get integral 0 to s ds. Okay, that is what you are going to see here. So substituting dou sigma z by dou z in equation 1, you get this equation t in terms of t into x, in terms of t into y, and then you try to add the equation. So you are going to get this equation integral 0 to s dou q by dou s into ds equals to minus of sx ixx minus sy ixy by ixx I by y minus I square xy, integral 0 to s tx into ds minus sy iyy minus sx ixy divided by ixx I by y minus I square xy, integral 0 to s ty into ds. Okay, so this is my equation what we got here. And one more thing also you can understand here from this previous one. So when you try to integrate the left term, and you are going to get integration q, and that is if the origin for s is taken at the open edge of the cross section. So at q equal to 0, q equals to 0 when s equals to 0. So this equation becomes now qs minus q naught. The left side you are going to get qs minus q naught, but this q naught for the open section beam you can consider it as 0, and then you left with only qs in the left side of this equation after integration. So by writing that, qs is equals to minus sx ixx, and this you are going to get the equation. So this is a very, very important equation. This is nothing but the formula for shear flow in open section beams. Shear flow in open section beams. Okay, so this is the formula which we have to use for solving the problems. And to understand also, if you want to try to remember this formula, you can take it as minus c integral 0 to s t into x into ds minus capital D integral 0 to s into t into y into ds. You can consider where c is nothing but this constant and d is nothing but this constant. This is only for remembering this one. Okay, so if you have axis of symmetry, and you can substitute the product of inertia ixy as 0 here, and then it will reduce, ixx will get cancelled and you get sx by iyy, and here also sx ixy you get cancelled if any axis of symmetry is there, and iyy gets cancelled, and you left with sy by ixx into integral 0 to s ty ds. So this is the formula for shear flow in open section beams. Okay. So this is the formula for shear flow distribution open section beams, which you have to remember for solving the problems of shear of open section beams, either to find out shear flow distribution or to find out shear center. So that's all from today's session, and in the next session we are going to solve problems using this formula on shear flow in open section beams. So thank you everyone for watching.